Let's look at some word problems. The formula for the length of a circular arc can be used to analyze the motion of a particle moving at a constant speed along a circular path. So we're going to take a look at linear and angular speeds. Consider a particle moving at a constant speed along a circle arc of radius r. If s is the length of the arc traveled in time t, then the linear speed v of the particle is arc length over time, or s over t. Moreover, if theta is the angle corresponding to the arc length s, then the angular speed, this is omega, of the particle is central angle over time, which is theta over t. Note, linear speed measures how fast a particle moves, while angular speed measures how fast the angle changes. To establish a relationship between speed v and angular speed, we're going to divide each side of the formula for arc length by t. So we're going to see s equals r times theta, so we used that previously. And so we're going to see more of this. S of t equals the radius times theta over time. That's the one we're going to use. Then you may see v equals r times omega. So we're going to find the linear speed. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the top of the second hand as it passes around the clock face. So we know that one revolution is 2 pi times r. Okay, r is 10.2, and so we're going to just multiply it through. S equals 2 pi times 10.2, so that is going to equal 20.4 pi centimeters. Now we have to remember that time is 1 minute, and we're going to say instead 60 seconds. And so we're going to use v equals s over t. In this case, we solve for s here, right, over here. And so we can say this is 20.4 pi centimeters over 60 seconds. And so when you find the answer, this is 1.07 centimeters per second. Okay, so we just solved it in pieces. So another way we could have done it is like in the box that I had earlier. We can just say v equals r theta over time. So radius we know is 10.2. And then theta, we went around one full circle. So that is 2 pi over the time of 60 seconds, right? Second hand. And then so you would get the same answer. So try the example. The second hand of a clock is 8 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. Okay, so if you tried it out, r is 8 centimeters. We went around one full circle, 2 pi over 60 seconds. So it ends up being 16 pi over 60, or reduces to 4 pi over 15. And so that's what you would leave it in for me. And then if you plugged it into a calculator, like if WebAssign wants a precise answer or around a decimal place, then you would get 0.84 centimeters per second. Let's find angular and linear speed. The blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. So we need to find the angular speed of the propeller in radians per minute, and then we're going to find the linear speed of the tips of the blades. So if we're looking at the angular speed is theta over time. And so in this case, it is 15 revolutions per minute. So that's 15 times 2 pi, right? One revolution is 2 pi, and then 15. And then so that ends up being 30 pi radians per minute. And so that is our angular speed. Now to find the linear speed, this is the v equals the r theta over time. So our radius is 116 feet long. So it's 116 times this, the 30 pi, over 1 minute. Okay, and that's 30 pi feet. So when you plug this in a calculator, you're going to get 10,933 feet per minute approximately. Okay, so it's just a matter of plugging it into the formula and hopefully that helps out. So I want you to go ahead and try this next example at the top. The circular blade on a saw has a radius of 4 inches and it rotates at 2,400 revolutions per minute. Find the angular speed of the blade in radians per minute and find the linear speed of the edge of the blade. So try this out, you would have gotten 4,800 pi radians per minute, and then when you find the linear speed, that is 19,200 pi inches per minute, or 60,319 inches per minute if you plugged it in a calculator. Last thing we're going to do is finding the area of a sector of a circle. So given the circle of radius r, the area of a sector with center angle theta is area equals 1/2 r squared times theta. So let's try this example. Area of a sector of a circle. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. So we need to know that formula. A equals 1/2 r squared times theta. So r we know is 70 feet. And we need to figure out what theta is. Currently, we have it in degrees, and we remember that we have to have it in radians. So it's pi over 180 degrees. So when we convert it, that is going to be 2 pi over 3 radians. So now we can use a formula. A equals 1/2 times the radius, 70 squared, times 2 pi over 3. So let's see what I can cancel out. 2 can cancel the 2. So we have A equals 70 squared, that's 4,900 pi, and then all over 3. Okay, and that's fine there. Like that would be an okay answer, 4,900 pi over 3 square feet. And then again, if you have to plug it in the calculator, because that's what the answer that WebAssign is looking for, then you would get 5,131 square feet. So try this example. A sprinkler sprays water over a distance of 40 feet and rotates through an angle of 80 degrees. Find the area watered by the sprinkler. Okay, if you tried this out, you would have gotten 3,200 pi over 9 feet squared, or 1,117 feet squared.